Hello friends. In this video, I want to share with you the implementation of my next idea, the essence of which was to increase the time of one of my Ecoflow charging stations, the Delta 2 model, but without incurring unjustified costs. By costs, I mean buying the official battery, which at the time of this video costs around $850. I managed to save about 70% of this amount while getting the exact same result. Next, you will see a review and capacity testing of the battery I chose as additional storage, the connection method, and the actual result of this upgrade. This also won't be without automation and Home Assistant, the essence of which I will also explain in detail. More details, and for now, as usual, I ask you to like this video so that more people interested in this topic can find it, and subscribe to my channel if you haven't done so before. So let's begin. The task I set for myself was to double the usable capacity of the Ecoflow Delta 2 charging station. So I chose a 12-volt, 100 amp-hour lithium iron phosphate battery. To avoid waiting too long, I selected a manufacturer promising delivery from a European warehouse within a week, HumsiENK, about which I had already heard good reviews. Besides it, I also needed a sufficiently powerful charger, which was ordered in advance from Aliexpress. You will find links to it and to the battery in the description under the video. Battery type: lithium iron phosphate. The battery consists of 4 A+ grade prismatic cells. Nominal voltage: 12 volts. Capacity: 100 amp hours. Stated energy: 1280 watt-hours. Maximum charge/discharge current: 100 amps, which corresponds to a 1C capacity rating. Recommended current for charging/discharging batteries of this type: 0.5 C, i.e. 50 amps. Stated cycle life: 6,000 cycles while retaining 80% depth of discharge. Smart BMS is installed with protection against overload, overcharging, overheating, or cell balancing. Supports Bluetooth control. Protection rating: IP65. Ability to build packs up to 4 S4P, that is 48 volts, 5 kilowatt-hours. Size: 260 by 168 by 209 millimeters. Stated weight: 10.55 kilograms. Important: this device is intended for energy storage and uninterruptible power systems. It cannot be used as a starter battery. Delivery was not long. Soon after placing the order in the Nova Poshta delivery service app, a notification about a new parcel appeared. For days after that, I had already picked up the battery from the branch closest to my home. The only point is that the weight of the parcel is less than 10 kilograms, while the stated weight of the battery is 10.5 kilograms. But we will return to this point later. This is what the box looked like that I picked up from the post office. Dense packaging cardboard, brand name. Weight: matches, about 10 kilograms. This is what its contents look like. The battery is firmly fixed with 2 inserts and does not rattle around in the box. Everything was delivered not only quickly, but also without any damage. This is what the battery looks like. It indicates a nominal voltage of 12 volts, type LiFePO4, and a usable energy capacity of 1280 watt-hours, which we will definitely check. Also on besides the brand name, it is indicated that a Smart BMS is installed here. There are versions with a regular one as well, without external control. On the other side, the nominal voltage is duplicated and the capacity is indicated 100 amp hours. This parameter should also be used as a basis when calculating the maximum discharge/charge current. For batteries of this type, it is 1C, that is 100 amps maximum, and 0.5 C, that is 50 amps recommended. Manufacturers specify the stated parameters for their specific models in the manual. But in general, for normal and long-term operation of the battery, you should not often subject it to extreme loads. On one of the side faces, there are also information stickers with the device's serial number. It will be useful if there is a warranty case, a list of parameters, and a QR code for connecting to the BMS. Jumping ahead, I'll say that I didn't need it, but it may be needed if you use an assembly of such batteries to connect to a specific one. Also in the box, there was a of screws for pieces for the battery terminals, plastic caps, and a manual. It is universal. It lists the entire model range of the manufacturer. There are mini, max, smart versions, and their variations, from 50 to 314 amp hours. To connect the terminals, M8 screw terminals are used here, which is standard for batteries of this type and ensures a reliable connection. As I mentioned, that includes 2 pairs of screws, which differ in length. You can choose the pair that will be more convenient for you, taking into account the current connection. You can also use the included plastic caps. Overall, the assembly made a good impression. The case is made solidly. Nothing rattles. There are no gaps. There was also no smell, which some products have. And this is a frame from the manual. As you can see, the table contains information for the entire battery line. The hero of the review is located in the table at the top left, the second to last column. Here the charge/discharge parameters are indicated. The manufacturer recommends charging with a current of 20 amps. This is good advice, but only if you have more than 6 hours for charging. Also, the protection trip thresholds, dimensions, and weight are indicated here. This is another summary table with general parameters, where the recommended charge voltage is indicated, 14.6 volts, the factory voltage and charge level, cycle life, self-discharge level, less than 3% per month, and so on. By the way, here the protection rating is indicated as IP67. The voltage at the terminals, which I measured before connecting to the charger, out of the box, is 13.2 volts. This is an expected and actually good result. Now let's get back to the weight, which I already mentioned a little earlier. The actual weight of the battery turned out to be 9 kilograms instead of the stated 10.5. Objectively, this is not a very good sign, but the capacity test that I will show soon will put all the dots over the I. Since I chose the model with Smart BMS, it's time to move on to the control application, which is available in the Play Market under the manufacturer's name. After installation, in the upper right corner, press the search button and connect to the battery via Bluetooth. Here you can assign it a name, which will be convenient if you have several of them. See the charge level. Out of the box it was 59%, the current voltage, temperature, the scale of which can be changed in the settings, current power and current. If you press the tile with the voltage value, a pop-up window will open containing information about the voltage on each cell. In this case, the maximum difference is only 0.003 volts, which is an excellent indicator. Let me remind you, for batteries of this type, a good value is a deviation of up to 0.01 volts. When you click on the temperature tile, a window opens showing the temperature of the BMS power transistors, MOSFET, and the battery cell temperature, T1. At the moment they are equal, which is logical. At the bottom of the application window, there are several buttons that switch between screens. Here we see all protection options for charging, discharging, and other modes when the battery is not connected to anything. In the parameters window, there is a status reset button and 6 protection trigger thresholds for charge and discharge current and temperature. On the last tab, a temperature scale switch and manufacturer information. To be able to charge the battery quickly, while still at the stage of choosing the battery itself, bought such a charger with the ability to adjust voltage and set current from 0 to 60 amps. The link to it is in the description under the video. Voltage, 14.6 volts according to the manual. I did not set the current to maximum, but at 46.5 amps, which is slightly less than 0.5 C of the battery, twice lower than the maximum, but higher than recommended. But let me clarify once again that for batteries of this type, a charge current twice lower than the nominal is considered a normal operating mode. Here is the data from the BMS, almost immediately after charging started and after 20 minutes, at 76%. Here we see that the temperature on the cells is currently 22 degrees Celsius, and on the power section, 29 degrees. It is considered that a difference of up to 12 degrees between the cell and the BMS is a good indicator, 12 to 25 degrees, average, and above 25 degrees, a poor indicator. An intermediate measurement at 83% charge, half an hour from the start of charging, 23 and 31 degrees Celsius respectively, and reaching 100%, 50 minutes after charging started, 28 and 36 degrees. Moreover, somewhere after 90%, I increased the current to 50 amps. No overheating is observed, as expected at such a charging current. Everything is fine here. Soon after that, The charging current began to decrease right before my eyes, and very soon the charge stopped. In the left screenshot, the current is still dropping. At that moment, it is already less than 37 amps, and 3 minutes later, the screenshot in the center, already 0, the BMS charging. The temperature of the power section had already dropped by 3 degrees relative to the last measurement, while the cell temperature increased slightly. A feature of such power supplies is a rather noisy cooling fan. Therefore, I immediately decided to implement power control for it in order to turn it off right after charging is completed. I will also show the implementation a little later in this video. I am interested in how much the battery can deliver under a load of approximately 0.1 C of its capacity. Therefore, I set the electronic load to a constant power of 120 watts. Since I was modeling real conditions of my case, I did not really let the battery rest. The discharge started literally 5 minutes after charging was completed. The application shows negative power and current values, meaning the battery is delivering them. The power section managed to cool down to 33 and the cells to 29 degrees Celsius. Another half hour later, to 29 and 27 degrees respectively. Why did I set such a load? Very simply, the Ecoflow to which I will connect it simply will not take more, and in fact even less. An intermediate result after 3 hours. The electronic load received more than 370 watt-hours of energy, the charge level, 71%, which corresponds to expectations, and the temperature dropped further. Almost 5 hours of discharge, 576 watt-hours of energy delivered, charge level 55%. The temperature of the power section is unchanged so far. The cells decreased a little more. And the last intermediate measurement, almost 8 hours after the start, 957 watt-hours of energy delivered, charge level, still 24%. The MOSFET stabilized at 27 degrees, the cells, 22 degrees. I was too lazy to wait further, so I left the test bench until morning. And here is what awaited me in the morning. In fact, the battery delivered 1,289.6 watt-hours of energy, which is even more than the stated capacity, despite some shortage in weight. The test lasted 10 hours and 45 minutes. I am more than satisfied with the result. Here is what the BMS shows. Voltage 11.4 volts. Cell voltage around 2.9 volts with a deviation of up to 0.083 volts. They will balance during charging. The temperature overnight equalized to room temperature. As I mentioned earlier, I use several Ecoflow charging stations at home, which are integrated into Home Assistant. You will find a video tutorial via the link in the description. It so happened that all the models have different capacities and power, and today's case concerns the most powerful one. I mean among those I have, the Delta 2. It is shown here in the left column. It is mainly intended for a refrigerator and several lamps, whose consumption can be neglected. The graph shows its standard operating mode, turning on at a power of slightly more than 200 watts for about 10 minutes. Then about 15 minutes of idle time. Thus, the power reserve of the Delta 2 is huge. The question here is solely about its capacity. Before starting all this, I conducted a test where I used a power supply with a UPS function and a small 12 amp-hour lithium iron phosphate battery. Reviews of both you will find via the link in the description. It is clear that this capacity would not have any noticeable effect. The principle itself was important to me. The output of this set was connected via a cable with an XT60 connector. I will leave a link to it in the description under the video, to the car charging or solar panel port of the Ecoflow. On the station, this port was configured specifically as a car charging input. This is very important, with a current limit of 4 amps, so as not to heavily load this small battery. What is the difference between the modes, solar panels and car charging? In the first case, the station will constantly draw energy from the port, mixing it into the overall flow, thereby reducing the power taken from the grid. In car charging mode, only when there is no external power, which is exactly what we need. And this is the power graph at the solar input. As I said, consumption occurs only when external power is. Power, slightly less than 50 watts. those same 4 amps, with small peaks, which apparently are related to the operating characteristics of the station. As we can see, the battery lasted about 1 hour and 40 minutes. That is about 80 watt-hours. Considering that the battery is in buffer mode, this is an expected figure. Now, to understand the essence of my task, I will show the graph of a full discharge of the station, which sometimes happens and which prompted me to implement this project. So, power outage and the start of discharge at approximately 2:27 a.m. level 99%. At the beginning of discharge, while a small backup in the form of a small battery is still working, the decrease in charge level is not as fast, but in fact it is not capable of having a significant impact. Next, the station's own battery is already working. Here you can see the midpoint of discharge. Exactly 5 hours have passed, level 50%. 10 hours from the moment of outage, charge level 2%, the station shuts down. So after that the level practically stabilizes until power is restored and charging begins. Here I have a slightly different setup. There is no power supply with a UPS function. I do not use buffer mode. I need the full battery capacity. But in this case, it cannot be kept constantly under voltage, so I will need to turn off charging after it fully charges the battery. This will also be implemented in my project. In parallel with the charging contacts, I connected the same XT60 cable to the battery. This system is already comparable in size to the Ecoflow itself, but it will take on the main load at the first stage of discharge. Now I will show and explain everything. For connection, I use the same XT60 port, thus I do not interfere with the station's circuitry. I mean those projects where an external battery is connected to the external battery connector using various tricks. In addition, I do not create extra load on the station's power section, since it does not need to charge another battery. It has its own charger. The system has been assembled and installed. It's time to move on to the software part. To control the charger, the easiest way is to use a smart plug with energy monitoring. After waiting for the moment when the battery was fully charged, I checked the power consumption, 12 watts, apparently for the operation of the charging fans. Based on these parameters, I wrote the logic, as usual grouping everything into a single package file, the link to which you will find in the description under the video. And now let's take a look at it. The first block is the recorder. I use the whitelist principle. Record only what is explicitly specified, and everything else is not stored in the database. This way I have all the data I need, and the database remains compact in size. In this case, I am only interested in power. The next block, not mandatory for this logic, is customization. Here custom names, type, display, and units of measurement for the sensors are defined. All of this can also be set manually through the interface. But for me, it is more convenient and faster this way. The metrics for turning charging on and off here will be 2 template sensors, which we will now go through. The first is the start of the charging process, which is tied to the event of power restoration. This is tracked using a sensor based on a Zigbee door sensor and an optocoupler, in my case, several of them. A link to the review of such a sensor is in the description under the video. The 2-minute delay is needed to ensure that the plug reliably reconnects to the network after power is restored and to separate the startup impulse from devices that turn on at the moment the city grid power appears. The second is the end of the charging process. It is based on 2 conditions: power consumption less than 20 watts and the smart plug relay turned on. Here, a 1-minute activation delay is also set, and accordingly 2 simple automations. The first, for turning on, which will trigger when the start sensor is activated 2 minutes after power restoration. The second, for turning off, which will turn off the relay and accordingly the charger connected to it 1 minute after the charging process ends. This makes it possible not to keep the battery constantly under voltage, that is, to use not buffer mode, but a normal mode, charge, discharge. And for everything to work as intended, you need to make sure that the plug is set to the mode off for the behavior setting after power restoration. Here is the moment of charging. Power 662 watts. The shutdown sensor is inactive. The plug relay supplies power to the charger. In the diagram slightly above, you can see how the Ecoflow operates. Its battery is fully charged, and everything it receives at the input is delivered to the load. And here the charging process has completed, the relay turned off, the battery stands fully charged and waits for the next power outage. And this is the moment of a power outage. The Ecoflow activates the car charging input as it thinks. By the way, this does not happen immediately, but after the station discharges by a few percent. In the first screenshot, you can see that it is currently delivering 192 watts. That is the moment the refrigerator is running, and it is receiving a little over 100 watts. The second screenshot, the current port settings, here I set the maximum, 8 amps. And the third, this is the battery BMS, which shows that it is currently discharging at a current of 8 amps. That is why I conducted the test at a load of 120 watts, even slightly more than is needed in practice. This is what the animation of this process looks like in the interface. Now let's analyze the discharge of the Ecoflow battery. I have not yet discharged it completely, but in my opinion this period is also sufficient to understand the difference before and after. As we remember, previously the discharge lasted 10 hours, exactly 10% per hour. Now, outage at 10 hours 40 minutes. Charge level, 99%. As I already said, the car charging port is not activated immediately, but after some time, so the station managed to discharge to 97%, and it stayed at this level much longer than at 99 and 98%. Then the level rose again to 98%. Further, the discharge trend is clearly visible. First -1%, then a return, but the duration of this return becomes shorter each time, until finally the station drops to the next step down. Here you can see the charge level value more than 2.5 hours after the power outage, 97%. Previously it would have been 75%. Here are the states more than 3 hours after the outage, a drop to 95, then returns to 96%. That is, the main load is now taken by the external battery. The station remains almost fully charged. And here is the moment of power restoration, 4 hours after the outage. At that moment, the station showed 95% charge instead of 60% as it would have been before. A few minutes later, it fully returned to its original state. By the way, this scheme, in case of not very long outages, will allow keeping the station's main battery in a gentler mode. For example, charge up to 80% and discharge to 20% and essentially operate only at the expense of the external one, which is much easier and cheaper to replace. Here is the charging graph of the external battery. After power is restored, the relay turned on. The power is about 660 watts, and after 40 minutes, after a full charge, the battery is ready for operation again. As a conclusion, this is what, at the time of creating this review, the power graph on the car charging port looks like, overlaid on a single time scale with the station battery charge level. Here you can see that earlier, when the test bench was installed, it did not have a visible effect on the discharge rate and was quite short. But for the test, I did not need more. Now it is visible that the power received from the charging port in duration coincides with the battery discharge. Since installation, there have not yet been long outages. The discharge itself has significantly slowed down, especially at night, when no one is using the refrigerator. The goal I set for myself, to increase the station's operating time, has obviously been achieved. In addition, it is possible to switch the station battery to a gentler mode, for example from 20 to 80% charge, and significantly reduce the charging power. That's all. I hope this video was interesting and useful for you. I would appreciate your likes. They help promote the video on YouTube. If you are not yet subscribed to my channel, now is the perfect time to do it. In the description under the video you will find all the necessary links to stores where you can purchase the devices shown in the video, the presented package, as well as my social networks, Telegram channels, and a group for discussing smart home questions. Join us. It will be interesting. Thank you for your attention. See you next time, and peace to everyone.